Right. So here's a quick review. So we started talking about something called the sample mean, and what this discussion is actually leading towards is called the weak law of large numbers, which is something that I'm sure many of you may already be familiar with. Okay. So the first thing we defined in this subtopic are something called IID random variables. So IID stands for independent and identically distributed. So we say that x1 through x sub n are IID if all of these random variables are drawn from exactly the same distribution, right? The same PDF or the same PMF. And moreover, are independent of each other. So the marginals are all the same, and all of the random variables are independent of each other. And then we say that the random variables are IID. Now, the next thing we started talking about is given realizations from these IID drawings, right? So I pick the random variables drawn independently and identically from a single distribution. And given those realizations, I wish to estimate the mean of that distribution. Okay. So, given those observations, x1 through xn, the first thing we did was, Katie, let's do an example in terms of maximum accurate estimation. So this example that you see on the screen is the fact that if x i's were drawn IID from a Gaussian distribution, which has a certain mean mu and has a certain variance sigma squared. So I know what the distribution is. Given that distribution, the maximum likelihood estimate of the mean actually turned out to be this sample mean that you see on your screen. So this equation one, if you will, right? So this was the sample mean, which turns out to be the maximum likelihood estimate of the mean when the random variables are IID and random variables are drawn IID from a Gaussian distribution with a certain mean and with a certain variance. Then the maximum likelihood estimate of the mean is just a simple averaging of the observations. Okay, that's what we did. And then we said, Kitty, regardless of actually whether the random variables are drawn from Gaussian or not, this sample mean that we've computed turns out to be a good estimate of the mean, right? And this is a discussion that we're going to start today with. I mean, why is this a good estimate of the mean? And there's a lot of theory behind it. We're just going to just scratch some of the surface. Okay, so this sample mean is, as you see on the screen, is equation number 2, if you will, is just taking up n drawings from that distribution, okay, and taking the average of it. And then I say, KG, if x1 through xi's are all IID, this sample mean turns out to be a good estimate of the mean when n is large. As n keeps on increasing, the estimate is going to get better and better and better, right? And which makes intuitive sense as well. I mean, when you do polls or when you do estimations, that's what you do. I mean, you take a sample and you start computing the average, right, of the sample. And as the sample size gets large, as the sample size gets larger and larger, you would tend to think that the estimate gets more accurate, right? That's something that your intuition also tells you, uh, which may also be, I mean, polls, America में भी इतने सारे हुए, right? You have polls that take place, and that's based on getting a large enough sample of a population, and from that sample getting some estimates, and the sample size has to be large, and that's all of those surveys are based on those ideas. Like how large do they have to be to satisfy a certain accuracy criteria? Okay, now this leads to something called the weak law of large numbers, the sample mean. And let me start our discussion today with that law. So this is the weak law of large numbers. Or law of large numbers, as you may be more familiar. Law of large numbers. Right, so this is, okay. So how many of you have heard of the law of large numbers? Nazish, have you heard of law of large numbers?
I'm not sure.
Not sure? Shoaib, have you heard of the law of large numbers?
No, sir.
Okay. G. Mohsen?
Sir, if you take enough samples of any random variable,
Yeah.
so the values start to resemble the value of the mean.
Right. So where did you hear about this this law of large numbers before this?
Sir, I think I've just heard about it or seen it enough times.
Okay. I mean, can you try to give me an idea? Where have you seen it enough times?
So maybe in statistics in undergraduate courses.
Okay. Right. So you have the same, mostly you took the same courses as everybody else, right? Or maybe you took some extra courses in statistics?
So maybe statistics was an extra course.
Okay. Okay. Acha, so let me try to phrase the law of large numbers here, right? So like I said, Kiri, as I start increasing n, the sample mean turns out to be a good estimate of the actual mean. Okay. Now, when I say good estimate, or when I say Kiri, sample mean is going to get closer and closer to the actual mean as n increases. Now, what do I mean by closeness, right? So that's something I need to define, okay, or I need to formulate or quantitatively describe, okay. First off, this S sub n, I mean, is that random or is that deterministic? Kyun, Khalid? Shoaib, do you think S sub n is random or is it deterministic?
Deterministic. Expected value is deterministic.
Is S sub n?
Yes. So we are taking the mean over here, and we know that expected value is deterministic.
Okay, but it's not the expected value.
Okay. Sum करके we are divided by n.
Yeah. So what am I summing up? I'm summing up random variables, right?
Okay. So ठीक है. So that then this will be random because we're summing up random variables, which itself जो answer आएगा that will be random.
Exactly. So I'm summing up random variables. I'm taking the average of random variables, and that average must be random as well. Why? Because that average, which is sample mean, is a function of things that are random, and functions of random things are always random as well, right? So therefore, the S sub n is a random variable. Okay. All right. Uh, if this is a random variable, that means this random variable has some mean and some variance, right? Let's try to compute what the mean is, right? So let me first of all try to compute the expected value of S sub n, right? And remember, this S sub n is actually indexed by n. So therefore, S1 is a different random variable than S2, which is a different random variable than S3, and so on and so forth. So the random variable is indexed by this n variable here, okay, n parameter, okay? As n changes, the random variable changes, okay? What is the expected value of the random variable S sub n? So for that, I will just plug in the definition of S sub n. So this is 1 upon n, summation, expected value from I equals 1. So summation from I equals 1 to n, x sub I. And because of the linearity of the expectation operation, the summation can come out. And 1 upon n comes out as well, right? So n is not random, n is deterministic. And this is expected value of xi. Okay. What is expected value of xi? Right. So we know because there are IID, so we know that expected value of x sub I is equal to that statistical mean, mu, for all I. No matter what I is, the mean stays the same, right? So what is the expected value of Sn turns out to be? If that's the case, if expected value of xi equals mu. G. Mohsen?
So mu.
Mu, right? So there's inside summation, each one of the terms is mu, which is being summed up n times. So that is n times mu and divide by n, it just turns out to be mu, right? So what that means is that the sample mean, if I'm using that sample mean as an estimate of the statistical mean, the average value of that sample mean, which is actually a random variable, the average value I know for sure is equal to mu, right? And that's why you may read in some textbooks, and actually in our textbook as well, the sample mean is often called an unbiased estimator of the mean. And the reason why it's called an unbiased estimator is because the mean of the estimate is actually equal to the thing that you're trying to estimate. Okay? So let me say this again. The reason why it's called an unbiased estimator is because the mean of the estimate is equal to the thing that you're trying to estimate, right? So the average value is equal to the thing that you're trying to estimate, right? Now, how do I figure out, Kitty, till mean to same agya? I need to figure out what the deviation of the estimate is around the thing that you're trying to estimate, right? In order for me to do that, I will just simply compute the variance of Sn, right? And that will give me an idea of a rough idea of how much the deviation is from the mean, and that is the variance. Okay, so the variance of Sn, what is that equal to? If I add two random variables which are independent of each other, right? What is the variance of the sum of those two independent random variables? So this goes back to the thing that we did on correlations, right? And covariances. Okay, it turns out if I add two independent random variables up, the variances of those sum up. Okay, and if I have a sum of any sum of a number of independent random variables, the variance of that sum turns out to be equal to the sum of the variance of each individual random variable. Okay, and that's a result that you can easily prove because of the fact that because they're independent, the covariance is 0 and the cross terms just go away. And सिर्फ उनकी जो variance is समान हो जाएंगी. ठीक है? And I'll not derive that result. I'll let that be an exercise, if you will, if you have not done it already. Okay. So this variance of Sn turns out to be equal to 1 upon n squared. And then this is the summation I equals 1 to n variance of xi, right? So that's a result that I'd let you try to prove yourself. It's not hard, actually, it's very, very easy. And it turns out, okay, this turns out to be equal to 1 upon n squared. And the variance for each and every one of the random variable, let's say, is sigma squared, right? So that's information that's given to us, right? So therefore, this turns out to be n times sigma squared. And what is this turn out? This is sigma squared by n, right? So now that should give you a clear indication, or at least an intuitive indication of why this estimate is going to get close to the real value as n keeps on increasing, right? Can somebody explain that to me in plain English, why that happens? Josefa, what do you think?
So in plain English, if we're talking, then basically, if we're taking more and more samples, then we're more and more sure about where the mean of the variable lies, since we're adding, more and more values now. And right. Mathematically, we can see that as n approaches infinity, our sigma squared goes to 0, because of which there's no variance. And
Good. So intuitively, that's an explanation, which is as I keep on increasing n, the variance of Sn keeps on decreasing, right? The mean stays the same. Mean is not dependent on n. The mean stays the same. So the mean stays the same as mu. And as I keep on increasing the number of samples I have in the computation, in the mean estimation, the variance keeps on decreasing and decreasing and decreasing. And as the variance keeps on decreasing, I would expect with a very, very high probability that my mean is going to reside around mu. Okay? And that's the underlying principle or underlying principle on which the weak law of large numbers is based. Okay. Now, when I said, and let me discuss that next. When I said, okay, the mean is going to, sample mean is going to be close to the actual mean. Okay. I need to first of all describe that closeness, right? What do I mean by that closeness? That closeness, it turns out, has to be defined in a probabilistic fashion. The reason why it has to be defined in a probabilistic fashion is because S sum n, the sample mean, is actually random. Okay? So उसकी कोई ना कोई distribution है, और probability के हिसाब से मुझे कोई clauses define करनी पड़ेगी, and that I'm going to define that as a measure of closeness is the probability. So let us look at the probability that Sn minus mu absolute being greater than epsilon. Okay, the probability that the absolute difference between your estimate and the actual mean is greater than some small value epsilon, right? If this probability, so if this probability is small, what can I say? क्या ख्याल है? If this probability turns out to be small, what do you think? So what am I saying? What I'm saying is, yeah, this is mu, right? The thing that I'm trying to estimate. This is mu plus epsilon, and this is mu minus epsilon. Okay, and I'm saying that the probability that my S resides outside of this interval, right? If that is small, then I'd say it's close. Somebody raised their hand. Josefa?
Sir, I just want to say that if the probability is small, this means that the difference between mu and the sample mean is less than epsilon, in which and implying that it's very close.
There's closeness. So that's a measure of closeness that we can define. Excellent, right? So if this probability is small, then we can say, okay, we can say that, so that Sn is close to mu, right? And actually this is for small alpha, or for small epsilon, right? If this condition is satisfied, if the probability is smaller and smaller, and we can say, yeah, the estimate is close to the actual mean. The estimate is not exactly equal to the actual mean, but is close to the actual mean. Okay? All right. Is there some way we can bound this, or can we compute this probability somehow? Right. The problem here is that we don't want to restrict ourselves to any particular X, right? We want to derive a general result, right? Which is applicable regardless of what distribution X follows, right? Jo marzi X ki distribution ho, right? As long as it's IID, we want to generalize this. We want to derive a general result, right? So this is a tail probability, okay? So the tail probability, we want to have an estimate of this probability without knowing the complete PDF or the complete distribution of the random variables. Some parameters of the random variables maybe, but not the complete distribution. Is there something that we've done in the previous chapters which would help us in estimating this tail probability? Ji Shoaib.
Sir, Chebyshev inequality.
Excellent, right? So that's exactly what we've done. So the Chebyshev is thak karke is going to apply to this problem, right? So using Chebyshev, Chebyshev's inequality, what we can say is that the probability that the absolute value of Sn minus mu being greater than epsilon is less than equal to, Shoaib, can you remind me what the Chebyshev inequality was?
So sigma square over epsilon naught ka square.
Yeah, so this was not sigma squared, because sigma squared, remember हमने x की define की हुई है. This was the variance of the random variable in question, which is now Sn, not x. Okay? So this was the variance of Sn, divided by epsilon squared. Okay. And the variance is something we've derived already, right? So this is equal to sigma squared divided by n times epsilon squared, right? And this gives rise to the weak law of large numbers, which just says okay, as n goes to infinity, or as n is large, what happens to this probability? What happens to the probability that Sn minus mu is greater than epsilon, where epsilon could be any small number, right? Not 0, but any small number, arbitrarily small number. What happens to this probability? This probability can be made arbitrarily small if I choose n large enough. Okay, as n keeps on increasing, no matter how small epsilon is, as I keep on, no matter how small epsilon is, as long as it's fixed, if I keep on increasing and go on increasing, I can arbitrarily reduce this probability all the way up to 0. Okay, to any small number all the way up to 0. Okay, and that's the weak law of large numbers. So the weak law of large number just says there are many notations, there are many definitions, equivalent definitions. I'm not going to talk about all of them. So the weak law of large number just says okay, in the limit as n goes to infinity, the probability of Sn minus mu being greater than epsilon is equal to 0 for any epsilon is greater than 0. Right? This applies for any epsilon greater than 0. Epsilon can be arbitrarily small. Arbitrarily small. Any small number that you pick. Okay, this is going to be satisfied. Okay. So this is the weak law of the statement of the weak law of large numbers. Okay. Now, why is it called the weak law of large numbers? Or in order to understand that, let me say something else about this statement. Now, lots and lots of students confuse this statement with this statement. That limit n going to infinity. So they think this statement implies that limit n going to infinity as n is equal to mu. Right? So does this imply that? I mean, so I've given away the answer actually. When I say lots of students have this misunderstanding, so that this is a misunderstanding. Can somebody try to tell me why this is a misunderstanding? Or how many of you would have thought the same? Right? Where this boxed thing actually implies the right thing. Right? So I have two people who are the most honest here, because the first time I actually, and then that's very natural, actually, at least 3, right? Right? So I'm telling you that's not true. Okay? Why is it not true? इसके ऊपर जरा कोई light shed कर सकता है? Those of you who did not think about this that way. क्यों Ghazi? So Shaib, I'm going to come back to you. Sorry. Ghazi, any thoughts?
Not at the moment, sir. I just started. I just came, so I'm kind of behind. Sorry.
Okay. Shoaib, you can go ahead, please.
So because we are dealing with probabilities, so mu can be 5, or Sn can be 5 and mu can be 10, and mu can be minus 10.
Yeah.
So they are not equal, they are very far away, but on the opposite ends, we can still obtain 0.
I'm saying the probability is 0. So when I say the probability is 0 for any epsilon, so epsilon, let's say I choose epsilon to be 10 to the power minus 20, right? So arbitrarily small number. Okay, and the mu is 10, right? What I'm saying here is that as n goes to infinity, the probability that Sn is outside of the interval 10 plus 10 to the power minus 20 or 10 minus 10 to the power minus 20 is 0. इसका मतलब इसके अंदर रहने की probability 1 है. Right? So what this box statement is once again saying is that the probability that Sn is approximately equal to mu When I say approximately, इसका मतलब कि mu plus epsilon, mu minus epsilon के दरम्यान में, the probability that mu is going to stay in there is actually equal to 1, right? Outside of this interval, the probability is 0, right? क्या उसका ये मतलब नहीं जो right statement है? मोहसिन आपका हाथ खड़ा था जी.
सर बॉक्स वाली स्टेटमेंट आपने जिस तरह कहा है कि वो डिग्री ऑफ रैंडमनेस खत्म कर दी उसके अंदर, राइट? सर्टेन कर दिए प्रोबेबिलिटी को कि वो 0 पे इक्वेट होती है. जो रेड वाली है probably वो ये कह रही है कि म्यू की वैल्यू चेंज हो सकती है with the value of Sn.
No, mu stays constant.
So फिर मेरा कोई explanation नहीं.
Explanation उसकी anybody else?
But sir,
What do you think? जी शोएब.
Sir, but if you say that it's within the interval, that doesn't mean that Sn is equals to mu. It's interval में तो है, but it's not equal to mu.
Okay, good. Interval में तो है, but that does not mean Sn equals mean. Nice. And the interval, there's a definition of an interval. That's the first thing here. Okay, there's always a definition of an interval. Right? Okay, the epsilon has to be greater than 0. Can be arbitrarily small, but is not equal to 0. That's the first thing. Okay, so the Sn is always going to be within mu plus epsilon and mu minus epsilon, where epsilon is not necessarily 0. Okay, so when we're saying what this means is the probability. So let me not use red here, because what this means is that the probability that Sn resides in this interval, mu minus epsilon and mu plus epsilon, right? This approaches to 1. That's what it means for any epsilon greater than 0. So is equal to 1. In that limit. So these statements are equivalent. Okay. So that's the first distinction, right? So I'm always going to be talking about an interval, mu minus epsilon, mu plus epsilon. Okay. And that's why this is called a weak law of large numbers, right? That's the reason why it's called a weak law of large numbers. Okay. There's a strong law of large numbers as well, which we're not going to do here. Okay. But there's a strong law of large numbers as well, which gets rid of this interval, right? And even then there's a caveat, there's a nuance there. And that nuance is that when I say that the probability of something is equal to 1, or when I say that the probability of something is equal to 0 rather, when I say something, the probability of something is equal to 0, okay, there's still a probability 0 event that it could happen, right? So there's still a probability 0 event that it could happen, right? So probability 0 events का मतलब ये नहीं है कि they will not happen. They may happen. It's just that the probability of them is equal to 0, right? That's a distinction, right? So that's a very, very subtle point, and therefore this is not true. This is an incorrect statement here, right? And convergence is a whole another topic which we don't have time to go into. There are many types of convergence. This is the weakest type of convergence. When we say Kitty, the probability that Sn resides around in a small interval around mu that approaches to 1, that's certain type of convergence which is called the convergence in probability, right? So this type of convergence is called, that's just for your information. So this type of convergence is called convergence in probability. Right, and this is actually once again tied to one of the other points that I made a while ago, right? Which was, KG, what is the probability that a continuous random variable is equal to something? Right? What is the probability that a continuous random variable is equal to something. G. Mohsin?
0, 0.
That's 0, right? But when you do an experiment, right, you do get an observation, right? When you do an experiment, you draw or you run a random experiment and you observe what the continuous random variable turns out to be, it will turn out to be equal to some value. Okay? So therefore, even though the probability of that happening was 0, but yet you have actually observed it. Okay? The only reason why the probability is 0 because when you do the experiment infinitely many number of times, the number of times you're going to get exactly that value is going to be finite, right? So it's still probability 0, but it can happen. Okay, similar is the case over here as well. With probability 0, Sn may reside outside of this interval as well. Okay? All right. Questions here? I'll pause for a few seconds, if you will, for you to absorb this or digest this, if you will. Halka sir, I'll let you ask questions. Ji Mohsin.
Sir, how would you describe the weak law of large numbers in words?
So the weak law of large numbers in words. Okay, so is going to be that the sample mean Sn converges to mu as n goes to infinity. Okay, or rather, I would say the sample mean Sn converges to mu in probability as n goes to infinity. Okay, so that's sort of a technical definition. थोड़ी सी हगी इसमें क्योंकि मैंने convergence का लफ्ज इस्तेमाल कर लिया. Mohsin, is that good enough?
Yes, sir, it's fine.
Right, so Sn converges to mu in probability. So that's a one-line statement of weak law of large numbers. Okay, and what that means is as I take the limit going to infinity, the probability that Sn minus mu is greater than epsilon is equal to 0. That's what it means mathematically. Okay. Right. Now, what is the implication of the weak law of large numbers? The implication of weak law of large numbers is that if you wish to estimate the mean of IID drawings, okay? Okay. So Nazish has asked me a question here. What can we say about the distribution of Sn if we know the distribution of X? Kya khayal hai? Anybody else? If you know the distribution of X, if you knew the distribution of X, what will be the distribution of S? How will you find the distribution of S? I mean, regardless of how tedious is going to be or not tedious is it going to be, I mean, what are the steps that you're going to use? Nazish, आप ही answer करने की कोशिश करें. If I add two independent random variables up, how do I obtain the distribution?
So a transformation वाली चीज.
Transformation में yes, independent. If I add two independent random variables up, so the distribution or the PDF of the sum is equal to what? Is equal to the convolution of the marginal PDFs. ठीक है? तो अगर तीन add करें तो फिर three-fold convolution करनी पड़ेगी. So here is you're going to have to do n-fold convolution, and that gets hard, but not for the case of Gaussian though, or for exponential even. I mean, हम थोड़ा सा देखेंगे बाद में. ठीक है? Gaussian के case में this will stay Gaussian. A linear combination of Gaussian random variables always stays Gaussian. Okay. Achha. Now the use of Chebyshev's inequality and the sample mean will allow you to get an estimate of how many drawings would you need if you are required to estimate mu with a certain confidence interval. Okay? And that Chebyshev is going to allow you to do that. So, Ji Mohsin, go ahead.
सर ये नाजिश के क्वेश्चन के ऊपर एक ऑब्जर्वेशन थी, क्या ये सेंट्रल लिमिट थ्योरम से एग्री करता है कि अगर नॉर्मलाइजेशन हुई भी है एसएन की तो वो बेल कर्व बन जाएगी डिस्ट्रीब्यूशन?
बिल्कुल. So central limit theorem this is going to approach a Gaussian as long as you subtract the mean from it. Okay. And the normalization has to be with respect to, if I remember correctly, with root of n and not of n, the central limit theorem. and that approach is a Gaussian distribution. Okay, so that's a tangent. So let's not go into this any further. Okay, Mohsen, I can talk to you about this later, right? So this is the weak law of large numbers, and the weak law of large numbers is fundamental. I mean, and the result is fundamental to the fact that we use this for estimating lots and lots of things by just using the sample mean, right? And which is not just a sample mean. We can estimate the probabilities using the sample mean as well somehow. Okay, let me give you an example for this. Okay, so let's say you're trying to find कि जी आपका random variable एक dice है which is not necessarily a fair dice. Okay, so there are 6 faces, and this is not necessarily a fair dice. We don't know that the probability, what the probabilities are, and you need to estimate the probability. How would you estimate the probability of, let's say, a 1 appearing on the face of the dice? किस तरह करेंगे? So how would you estimate a probability of a certain event? Ji Mohsen?
So the probability of that outcome divided by the probability of the sample space.
What do you mean probability of that outcome? I don't know what the probability of that outcome is. Right? The probability is something that I need to estimate. Josefa?
Sir, basically we'll carry out the event and see what appeared on the dice, and then carry out the event a number of times, and then we can find the probability that Mohsen just talked about.
All right. So what you're talking about, I believe, is computing the frequency. Right. So you do the experiment, like throw the dice lots and lots of times. Right, lots and lots of times, large number of times, and then you count the number of times that 1 appeared, and then you divide that number of times that 1 appeared by the number of experiments, by the number of times you threw the dice. I think that's what you were saying, right? So that's a relative frequency approach anyway. And remember, we said KG as and this is, I'm sure, something that's at least on the top of your heads. Yeah, I know that as I go on increasing the number of times I throw this dice, the probability is going to get more accurate and accurate. The estimate is going to get more accurate. Right? It turns out that's a consequence of the weak law of large numbers, or the law of large numbers, if you will. Okay? Here's how. So the implication, one of the implication for this is, okay, suppose you are trying to estimate the probability of an event A. Right? And this event is not necessarily the dice thing. I mean, this could be any event. I mean, this could be the probability that there's a death corresponding to a certain, corresponding to a COVID infection. Okay? So you compute the death rates, right? And how do you compute the probability of death, as you would have been following all along, is you just compute the number of deaths divided by the number of infections, right? And that's actually this relative frequency approach. That's like doing the experiment over and over again, and you just count the number of times the event of interest happened, or the event of interest occurred. Okay? So the way I can justify that this relative frequency is going to approach the actual probability is through the weak law of large numbers. How? This is how. So if this is A is an event that you're trying to, the probability for which you're trying to estimate, let us define a random variable xi as being equal to 1 if the event A occurs. So that's a mapping that I'm defining, and 0 otherwise. Right, so this could really be, if you're interested in the probability of a 2 occurring on the face of a dice, whenever 2 occurs in a random throwing, okay, you would say the 1 XA equals 1, XI equals 1, otherwise XI equals 0. Okay, and X1 is the first drawing, X2 is a second drawing, X3 is a third drawing, and so on and so forth. And every time you're just saying कि हुआ था या नहीं हुआ था. अगर हुआ था, this random variable is 1. अगर नहीं हुआ था, the random variable is equal to 0. Right. Then what is the probability of A? Then the probability of A is actually the probability that Xi equals Xi equals 1, right? Is that clear, right? So the probability of the event happening maps to Xi equals 1. Okay. And what can I say about the expected value of Xi? What is the expected value of Xi? What are the two values that Xi can take? What are the two values that Xi can take?
1 and 0.
1 and 0, right? So, and I just define average value kya hoti hai? 1 is the value that it can take multiplied by the probability of that random variable being equal to that value, right? So this equals 1, right? Plus 0 times the probability that Xi equals 0. And lo and behold, this turns out to be equal to the probability that Xi equals 1. Right? Which is equal to the probability of A. Right? So what I know is that the expected value of this Xi is actually equal to the probability of A. Right? Now, if I form this variable, which is mu n hat, as being equal to, चलो यहाँ मैं S कह देता हूँ, Sn being equal to 1 upon n summation I equals 1 to n xi, what will this converge to? The weak law of large number tells me that this will converge to what value? The expected value of xi. That's what the weak law of large number tells me. Right? So this is convergence because of weak law of large numbers. And what is the expected value of xi? Expected value of xi is just simply equal to, as we've seen in the line above, is just equal to the probability of A. Right? So what do I have on the left-hand side? The left-hand side is just simply the relative frequency. Because all you have on the left-hand side is just counting the number of times the event of interest happened divided by the number of experiments, right? So this is equal to the number of times event A occurred normalized by the number of experiments. And I know that this is E approaches to probability of A, right? So this is a consequence of the weak law of large numbers. The fact that this relative frequency is going to be an accurate estimate of the actual probability of something happening is a consequence of the law of large numbers. Okay, that's why we use it so many times, so often. Okay. Any questions here? Okay, so if you'll allow me, let's break for 5 minutes. Okay, pray Maghrib, and we're going to come back at 5:20. So this is the end of this chapter. There was some topics from chapter 7 actually. Okay. And I did not cover that chapter 7 in a lot of details. There were some things, khas taur pe IID random variables and this weak law of large numbers is from chapter 7. Okay. So this is when I'm going to end. There are other stuff that I used to cover but since we have a shorter semester this time around, I'm going to skip that content and jump to the next chapter, which is on random processes, right? So if there are no questions about this weak law of large numbers and its implications, I'm going to move ahead, right? No questions going once, going twice. All right, sold, right? So this is our next topic of discussion, which is random processes. Okay, so this is not what we want to do. Okay, so the random process is also something I believe that the majority of you, or every one of you, should be familiar with, right? Kahin na kahin random processes kisi na kisi form mein dekhe honge, right? And let me begin by just clarifying some notation from signals, if you will, right? So we used to have this x of t, and we used to have this x of n, and this corresponded to these signals, right? So these were signals in either the discrete time or continuous time. Okay, T was continuous time and N was discrete time. However, the signals that we're familiar with so far, at least as far as undergraduate signal systems courses are concerned, or DSP courses are concerned, they are all deterministic signals. And what I mean by that is that if you're given some parameters, you know that ye signal hai, to ye yahi hai. I mean, it would always stay the same. I mean, that's deterministic. You can say for certain what that signal is going to be, right? That's deterministic signals, right? But then in many practical applications, there are other signals which are not deterministic, but rather they are random, right? There's a certain bit of randomness involved in the signal itself. And the prime example of that is thermal noise. Okay, is thermal noise, right? Which okay, if I just start plotting the thermal noise, right, in one realization and the other realization, they will never be the same, right? Because the variation in that as a function of time, there's a certain element of randomness involved there, which I'm not able to predict. Right? So the signals are random as opposed to what we were doing earlier than this, where we were talking about variables, and we said that variables are random, right? There was no notion of time there. Now we're introducing a notion of time as well. And when we introduce that notion of time, random variables transform into something which are called random processes, right? So if you just understand that, right, that things are going to be very clear. It's just the knowledge of all of the knowledge that we've done earlier, right? Generalized now to the fact that there's a notion of time as well. Okay, it's an extension of the same concepts. Okay, let me define some basic definitions for what random processes are. So if you recall from chapter 3, I believe, I mean, what were random variables? So let's do a quick review of that. Random variables kya the? So how do you define the random variable? Jimosin?
Sir, Kelly, a tool that maps the outcomes of an event to the real line.
Right, so good. So there is a random experiment, certain random experiment, right? And a random variable is actually a function, right? Which maps that random experiment, the outcome of the random experiment, to the real number line, to a value on the real number line. Okay? So this is a function that maps zeta, which is an outcome of the random experiment, to the real number line. To the real number line. and we used this X of zeta notation. I mean, and then from there we said कि असल में जो notation of X of zeta, implying that the value that X takes, the random variable takes, is actually a function of the outcome of the experiment, right? But then we said for notational convenience, we got rid of this functional description, right? When we just say this is an X, and where there is an underlying random experiment, there is an underlying outcome. We just don't care about that for notational convenience, and we're going to define all of the concepts without this notation. Okay, so that was random variable. What are random processes? By extension, I mean, random process is a simple extension of the same concept. Random process is also a function, and that maps the outcome of some experiment. Once again, there's a random experiment. Once again, corresponding to that random experiment is an outcome zeta. The random process is a function that maps that outcome to a function itself, to a signal, if you will, to a signal x of t, if it's a continuous time process, or a signal x of n if it's a discrete time process. Okay? So the idea is very, very similar, except that as opposed to random variables where the outcome was being mapped to a number, now the outcome is going to be mapped to a signal, okay, or a function, if you will, right? A function of time, right? And I would rather say it's a signal, okay? Because we're engineers. Okay, so that's a random process. And consequently, the notation that I can do, if I just follow the x of zeta notation, or if I were to extend this x of zeta notation that I had here, what do you think that notation for this random process should be? Just following up on that, or just extending that that definition? क्या ख्याल है? क्यों ज़ैफर?
Sir, maybe small x of that a function of zeta, and okay. Time probably.
And time? Probably. Why are you not sure?
I think it is because it's basically a signal, and a signal isn't like constant with time, so it should be time dependent too.
Good, right? So this is G. Mohsen. Go ahead.
Sir, capital X of t use kar sakte hain.
Right, but I want to first of all include this dependency of the outcome of the experiment as well, right? So this is the only extension. Okay, now the zeta is being mapped to a function of time or a signal. Okay, depending on what zeta is, I'm going to get different signal, right? So this is actually the random process is actually a two-dimensional function where the arguments are the time because it's a signal and the outcome of the random experiment because it's a random process. Okay, so this is that random process. It's just an extension of the same ideas, right? Now, this two-dimensional description that we've just defined leads to actually two equivalent interpretations, right? So this leads to equivalent interpretations. The first one is what I just said, actually. The first one is what? The first one is that if we fix the outcome, so for some outcome zeta 1, what is the random process? The random process is actually a deterministic signal. Is a deterministic signal. Right? What do I mean by that? Okay, you see, एक outcome आई है, so that means this is what the signal is going to be, right? And that signal is deterministic. If the outcome of the random experiment was something else, I would have gotten another signal, which was actually a deterministic signal. Okay? So it's actually a class of signals that I could have had depending on what the outcome of my random experiment is. Okay? Outcome 1 maps to this signal, outcome 2 maps to this signal, outcome 3 maps to this signal, and so on and so forth. Okay? Where the outcomes could be continuous as well. So I mean, this 1, 2, 3 was just for clarification or for ease of understanding. Okay? So for a fixed zeta, for a fixed outcome, you get a deterministic signal. So that's the first interpretation, and this interpretation जो ऊपर भी मैंने यही mention की थी. Second interpretation for me is more easy to understand, especially in the context of the analysis that's going to follow, which is what happens. So remember, in two-dimensional functions, को समझने के लिए वैसे भी, if any there was a two-dimensional function, in order to understand that, what we typically do is we fix one of the arguments and see what happens if I change the other one. And then I vice versa. Let's fix the other one and just change the second and see what happens. Okay? So in the first interpretation, I fix the outcome and see what happens as I vary time. As I vary time, it's a signal. Okay? What happens if I fix time? So this is a second interpretation, which is actually an equivalent interpretation. For a fixed time, let's say T1, what is that random process? What does that random process reduce to? Maybe I can have somebody else. Ji Shoaib.
Sir, any number on the real line.
Is that any number on the real line?
The numbers which this function capital X can take, actually.
All right. And is that deterministic or is that random?
That is random, I would say.
Good. Right. So that is random. Why? Because of the fact that the outcome are random. Outcome is random. So I fix time. I'm taking a slice in time. I just stand at one point in time and see what the random process can be at this particular time. And at that particular time, the random process could be either this, depending on what the outcome is, or this, depending on what the outcome is, or this, depending on what the outcome is. Right? But since the outcomes are random, the values that the random process can take at this particular time is also going to be random. Okay? And therefore, the random process at a particular time is nothing but a random variable. Okay? Does that make sense? So the random process is a random variable. Does it make sense?
Yes, sir.
Okay, this is just like, let's say if there was a deterministic signal, right? On my deterministic signal, let me just find out what that signal is at t equals 1 second. And I know that t equals 1 second, that signal could only be one value. And that's it. Okay, but if this was a random process, at that t equals 1 second, the signal could either be this or this or this or this, depending on what the outcome of the random experiment was. And that's why at that particular time instance, the random process is actually a random variable with a certain probability distribution or with a certain probability mass function and a QCDF and so on and so forth. Okay? So it's sampled at a particular time, the random process reduces to a random variable, right? So actually, that reduces to a random variable, and that will ease our understanding for everything that we're going to do next. Okay. Now, given this interpretation, if there are any questions about this interpretation, let me know. Here's a quick definition for you. I mean, given everything that we've talked about, right? And that definition is given an experiment E, some sample space S, the random process. Now, one thing I forgot to mention was a notation, which was, okay, just like in a random variable, we just use the capital X to represent the random variable, and we just ignore the fact it's actually a function of the outcome. We do the similar thing with random process as well. So as you see over here, I have just said that the random process is X of t. I've gotten rid of the dependency on zeta, knowing that that dependency is actually implicit. I just don't make it explicit, it is implicit. Okay? So from here on, whenever I say capital X of t, I'm actually referring to a random process. Okay? With the dependency on the random outcome as being implicit and not explicit, just as we did in the random for the case of random variables. Okay? So the random process X of t maps each possible outcome from the sample space to a function of time, to a signal कहते थे, as specified by some rule. So there is a certain rule that does that mapping. Just like there's some rule that maps the outcome to a real number in the case of random variables. And just like that, based on some rules, we're going to map the outcome to a signal. Okay, so that's the definition of a random process, right? Let's do quick examples. We have 10 minutes. Okay, any questions here? Feel free to interrupt me here. So what I'm doing next is just giving you some simple or some trivial, or perhaps in some cases slightly non-trivial examples of what those random processes could be. Okay, so the first example is rather trivial. We say, Kiji, suppose an experiment consists of a flipping of a coin. And so there are two possible outcomes of the random experiment. Okay. And what we do is, and this is sort of a pathological toy example, if you will, okay, we map the head to a certain function, and we map the tail to a certain function. So if zeta equals head, then we say the X of t, the realization of the random variable, is equal to some sinusoid, right, with a certain frequency omega naught. But otherwise, if there was a tail, right, otherwise X of t is another sinusoid, except that it has twice the frequency. Okay? And frequency shift keying may be one of the examples here. Okay, you flip a coin, flipping of that coin may be whether you're trying to transmit a 1 or a 0. And if you're transmitting 1, so what you transmit is a certain sinusoid with a certain frequency. If you're transmitting 0 or the other bit, so you just double the frequency, you change the frequency, increase the frequency. Okay, so that turns out the signal that you have is random. That could either be a sinusoid of a frequency omega naught or a sinusoid of a frequency 2 omega naught. Okay, so that's a trivial example. Let's do another sort of trivial example, right? So here, X of t equals a times sine omega naught t, right? Where omega naught is deterministic, but a is a random variable which is actually uniform, right? So a is a uniform random variable over the interval 0 and 1. Right? And the two interpretations that I gave you should be very, very clear. The first one being that if I if I fix A or the outcome, okay, outcome A turns out to be any number between 0 and 1 based on a uniform distribution, then x of t turns out to be a sinusoid which has an amplitude equal to that realization of A. Okay? And as A changes, the realization of the signal changes as well. So the amplitude of that sinusoid changes as well. So that's the first interpretation. The second interpretation being, okay, if I fix myself at t equals 0, or sorry, I fix myself at some t, right? And then I see कि यार at that t, what values can the random process take? Okay, that will be a range of values that the random process can take based on some probability distribution, which is governed by the fact that A is uniform. And you should be able to clearly see. So let me quickly have a quiz here, if you really understand. Okay, if t was equal to 0, what values of x of t can there be? X of 0, चलें. X of 0 is a random variable, right? X of 0 की क्या values हैं जो हो सकती हैं? क्यों अली? अली, क्या ख्याल है?
Yes, sir.
X of 0 is a random variable which I can, if I fixing the time, of course, is going to be a random variable. What values or what kind of a distribution would X of 0 follow? Right. Shall I as a right answer?
अगर t 0 हो जाएगा तो sin भी 0 हो जाएगा.
Exactly. So at time t equals 0, no matter what the realization of A was, X of 0 is actually equal to 0. Okay? So there's nothing random about that, by the way, X of 0. Okay? However, what about X of at any t? Like if I fix t, what PDF will X of t follow? Jameson?
So uniform distribution.
Exactly, it will still be uniform, right? It will still be uniform, but would that be uniform between 0 and 1? Jameson?
So I think it will be a scaled version of the uniform distribution between 0 and 1.
Exactly. Not exactly. It will be a uniform distribution. That I agree with you. Okay. Right. So Shoaib, it will not be a uniform distribution between minus A and plus A. It will actually be somewhere else. So it will be, as Josefa said, will be scaled by sine omega naught t. Because remember, t is fixed. If t is fixed, then sine omega naught t is a constant. Right? And depending on whether sine omega naught t is positive or whether sine omega naught t is negative, that will describe what your uniform distribution is, right? So it's uniform between, so here's the answer. It's a uniform between 0 and sine omega naught t if sine omega naught t is positive. Otherwise, is uniform between sine omega naught t and 0 if sine omega naught t is negative, right? So it really depends on what t is. But it will still be uniform. It's just that the uniform distribution has been scaled by A, by sine omega naught t. Okay, excellent, good. Okay, so here's the final example for this class. Right, which is slightly more involved, right? And actually, this x of t equals A times sine omega naught t is somewhat related to amplitude modulation that you may have come across in your undergraduate curriculum. Okay, communication systems, right? Okay, so the final example is that suppose you have an experiment, right? Now I'm going to make it slightly more complicated in the sense that I'm going to have randomness involved, not just because of one random variable, but multiple random variables. Okay. So suppose an experiment involves generating bits at random bits. And what are those bits? Those bits are B1, that's a bit which takes on either a value of 0 or a value of 1. Okay? B2, B3, and so on and so forth, all the way up to. So there are certain number of bits that you have in your arsenal, right? So that's a random experiment that you do. Okay? So you get a vector of zeros and ones, right? And then which is completely random, right? So BIs are either 0 or 1. Okay, so the random process that I defined is the following. The random process is 2 times BI minus 1 times sine omega naught t for all values of t between this interval. Capital T is less than small t is less than equal to IT. Okay, for some deterministic and constant omega naught and capital T. Okay. Now, does this look familiar? Something you should have done somewhere towards the end of maybe EE564. मुझे लगता है मेरी screen freeze हो गई है. So while I'm working on the screen, does this look familiar? No? Never seen this? Okay, so let's try to just visualize what this will be for one realization of the bits B. Okay, so let's say, okay, you do the experiment, you run an experiment, and suppose the realization that you get is the following, right? So suppose, suppose the random variable realizations are, so realizations is B1 equals 1, B2 equals 0, B3 equals 1, and B4 equals 0. And let's also assume that T equals 4 pi by omega naught. And what that means is that capital T is a duration of a bit, okay? And that duration is actually equal to twice the number of the cycles of the sinusoid of frequency omega naught, okay? So the realization of the random process is going to be the following. The random process realization is the following. So let's try to sketch it out. So here's a sketch. Okay. So for B1 equals 1, right? What is 2B minus 1? That's plus 1. Jimosen?
सर ये बेसिक सिग्नलिंग की तरह नहीं है, वंस और जीरोस को आप एक टाइम पीरियड के अंदर डिफरेंट एम्पलीट्यूड और साइनोसाइड्स के साथ आप भेज रहे हैं.
This is called something, there's a more specific name to this. This is binary phase shift keying, if you will, or amplitude shift keying. which I'm sure you would have studied in communication systems. क्यों? Mohsin, पढ़ा था communication systems में 380 में?
So it was nearly a lifetime ago.
Nearly a lifetime ago. So how about the other people here? So let me just sketch it out, right? So for B1 equals 1, this is going to be a positive sinusoid with a positive amplitude, and with there's two sinusoids, two cycles inside this capital T. So this is capital T. This is capital T here. Okay, and this corresponds to B1 equals 1, right? But because when B1 equals 1, so this is plus sine omega naught T. And then B2 equals 0. So this is 2 times 0 minus 1. So this is a minus sine omega naught T, right? So the minus sine omega naught T here is going to look like this. And 1 and 2, right? Where once again, this interval is capital T seconds. And this corresponds to what? B2 equals 0. उसके बाद क्या है? B3 equals 1. Okay. So B3 equals 1. मैं कोई गलती तो नहीं की? Yeah, I think that's fine. So when B3 equals 1, that once again is a positive sinusoid. Okay, B3 equals 1 is 2 times 1 is 2, minus 1 is plus 1, and it should be.
Sir, I think there's half a cycle more in the second one.
मुझे एक कोई गड़बड़ लगी. Yep. Oops. So this is right. So this was ये दो cycles होने, right? So this is one cycle, and this is 2 cycles. अब ठीक है?
Yes, sir.
All right, good. That's what was confusing me as well. Okay. Now B3 equals 1. So this is going to be a positive sinusoid. Right. And this is once again, this is T. And this interval once again is T. So it's twice the period. And this corresponds to B3 equals 1. And finally, B4 is 0. So it's again negative sinusoid. So this will be so 1, 2 finishes here. So this is B4 equals 0. And this is T again. Okay, so this is one realization of that random process. Okay. And now you can come up with that dual interpretation, two interpretations that I told you. The first interpretation being, as I change these B's, right, and there's a different realization of the random experiment. That means there's a different combination of those bits. This signal is going to change. And I keep on changing it, the signal is going to keep on changing as well. On the other hand, if I fix myself at a particular time, the random process can take on values which are random. Okay? Can somebody tell me here, okay, what kind of values would those at any particular time t will this random process fluctuate between? Let's say मैं यहाँ पे fix करता हूँ, and this is a time that I'm fixing myself to. ठीक है? So what do you think? यहाँ पे अगर मैं observe करूँ, तो random process values कौन सी ले सकता है इस जगह पे? Giuseppe.
Sir, basically the peak-to-peak amplitude of the wave at this particular instant.
Right. So what do you mean by that? Once again, I mean, what kind of a distribution would be this random process have? What are the range of values it could take? Is that continuous or discrete?
It will be continuous because the signal is continuous, so it could take an infinite number of values at this particular time instant, depending on the.
Depending on. Go ahead.
The bit.
Bit. Excellent. So depending on the bit, what are the values that the bit can take?
Oh, those are just 1 and 0.
1 and 0, right? So boy, when B1 equals 1, so फिर क्या होता है? I mean, this is exactly the realization that you're going to get. What happens when the only other possibility is B1 equals 0?
Mm-hmm.
And when B1 equals 0, the 2B minus 1 is just minus 1.
Okay. So we're basically just going to have two possible values that this could take.
So the random process at any particular time t can take at most two possible values. And when I say at most, क्योंकि कुछ ऐसी जगह हैं जहाँ पे 0 हो सकता है सिर्फ हमेशा, ठीक है? So it could either be, so this is, remember, this is +1 and this is -1. So at this particular point in time, which is the blue slice, the random process could either be +1 or -1. Okay, is that clear? And as I move along, I mean, it could either be plus some value or minus some value. I mean, which is not necessarily +1, depends on what time you're sampling it at, right? It's just like ये वाले जो time है, यहाँ वाले पे, here is always going to be 0. The random process will always be 0 at these boundaries, right? Regardless of what the outcome of the experiment is. Okay, and that should be clear. Okay. So here are, these were 3 examples. I'm going to stop here. Yeah, so there's a 4th example I'm going to put in my notes. I'm going to put them up on LMS anyway. Okay. You can go ahead and read, and we'll start with the mathematical basics tools in the next time. Okay. Any questions here? Ji Mohsin.
So wouldn't the random process take a scaled sinusoid, the value of a scaled sinusoid?
Yeah, but the scaling is by what? I mean, here's the point. The scaling could either be only +1 or -1. That's the whole point. Okay. The scaling is not continuous. The scaling is discrete. Okay. Either the scaling is with +1 or the scaling is with -1. Right? There are only 2 possibilities. So that's why it could not take an array or an amplitude, whole range of values.
We can say based on one single sample, you cannot determine whether it's B1 or a bit 0.
On a single sample? On a single sample, perhaps yes, if you know if you knew time t. If you knew capital T and you knew where you were sampling it at. लेकिन असल में communication में और बहुत सारे मसले होते हैं. I mean, there's a lot of noise here. So you have to do a lot more. When otherwise given a realization of a random process, give this realization of a random process, if I sample it at any time t and if I knew what capital T was, that is enough for me to know what the random variable was perfectly. Okay, think about that. Okay, so I'm going to stop.